Hello, friends. My name is Bill, and I'm here with my friend Peter.
Hi, everybody.
He's the CTO of Resurgent Technologies and co creator of this new and exciting memory management tool called Bitflux. Today's video is going to be on how Bitflux works, and we'll compare it between Bitflux and a standard system. So let's jump right into it.
So let's just talk about what we can see, what's on the screen here, right? And we're gonna go ahead and
Yeah.
press go on this display so we can watch it doing its thing.
Okay.
And this is an experiment that you set up, Bill.
Yeah.
So I'll let you talk about the tenets of it, but I'm just going to describe what we're seeing here. On the left is a machine with 2 GB of RAM, and on the right is a machine with 4 GB of RAM. And the only other difference between these two virtual machines is that the one on the left is running Bitflux. Um, you want to describe what they're going to do?
Yeah. So this was basically like a use case in which I was like, okay, well, this is a getting started for the day kind of thing. So I opened up a browser instance and I'll open up 10 tabs with 10 pages. And then I open up another browser instance with 5 tabs and 5 pages. And then the pièce de résistance is when we open up the ID app and then it shows some magic. But that's basically like, okay, now I'm ready to get started. Work. That's
Yeah,
that's the whole point and
yeah.
premise.
I'm like it's basically a simulation of I'm showing up at work, right?
Mm.
I'm going to open up a few web pages. I'm going to read the news. I'm going to look at Reddit because I'm a terrible employee. And then I'm sorry for anyone that looks at Reddit. It's not a dig.
Yeah.
No judgment here. But you do, right? Like you come into work, the first thing you do is you check your emails, you check websites, you check news sites, you load up quite a few web pages if you're anything like me, and then you get to work. You open up your IDE, if you're a developer, you open up Excel if you're an accountant, whatever. Um, so that's what's going to happen in the video. Um, at the beginning, we're just looking at web pages. So I'm going to take the opportunity to describe what you're seeing in the dials at the top here. These are metrics that we've developed that we believe will make it easier for people to understand how their memory is being used. And we're simplifying a lot of the numbers that you normally see, right? This bottom chart that you see on both these windows is about as complex as we think memory ever needs to be shown. If you drill down, there's like 65 metrics you can pull out of the memory system to see everything under the sun, including like buffer allocation and things that only mean something specific to a very specific person. Um, what we think is most important is the difference between allocated memory, which is what we're going to refer to as used from here on out, and unallocated memory, which is free. So in these top charts, that's all it is. Above the line is free, below the line is allocated or used. And that's there's like we make that distinction because if it's allocated and we run out of memory, then we have to do something, even if it's small, like freeing a cache page, before memory can be given to an application. And if it's free, we can give the memory to the application.
Mm-hmm. Yeah. So yeah, I thought it was curious. So looking at some of these gauges right now, um, we can see that like our access ratio in this gauge, I don't have the pointer, but in this
Yeah.
access ratio, we're accessing 64.2%, whereas the standard system's accessing 19.7. What exactly does that mean?
Yeah. So this is I think possibly the most interesting metric that I've ever seen about memory. This means of the allocated pages I have, how many of them are actively being used by the system?
Hmm.
If I have, the system on the left, right, we have 1.3 gigabytes used, and 64% of that has been accessed. That means 64% of this 1.3 gigabytes is actually being used by the platform. On the right, we have 2.7 gigabytes used, and only 20% of that
Yeah.
is actually being used by the computer to do its job, which kind of makes sense, right? You just have a web page open, right? Like What else does the computer need to do? It needs to be showing you its web page and maybe a few background tasks. So this metric is really interesting because this sort of uh, prompts us to have a new adage for memory. I was taught in like my IT days that unused memory, unallocated memory is wasted memory,
Yeah.
and I'd like to take that adage and alter it just a little bit. I think memory not being used for a task you care about
Right.
is wasted memory.
Right.
And that means memory can be free to me if I want it to be available for me to do my next big task, right?
Right. And yeah, I mean that totally makes sense to me. I think at this point in the video, we've opened. It looks like 9 windows. So we're getting close to open up to the next browser instance. But you can see that Bitflux used memory, we're at 1.34 gigs, and the used memory on the standard side, we're using 3 gigs, right?
Yeah.
Which I thought was curious only because Bitflux has 2 gigs and the standard system has 4. So is there a reason for that? Like why it's used memory is higher on the standard side?
Yeah, it's really simple actually, and it goes back to the adage we were just talking about. The standard community thought is that unused or unallocated memory is wasted memory. So the default memory caching choices in Linux is basically hold on to it if you ever looked at it, right? And these graphs reflect that. So if you look at the one on the right, used just sort of grows
Mm-hmm.
pretty much linearly
Yeah.
with whatever tasks we open, right? And if we stop opening new tasks, it'll plateau, but it doesn't really go down. It's not really designed to go down. It's designed to hold on to everything you looked at in case you look at it again. And that's an interesting thought, and it sounds good on the tin, right? Because
Mm-hmm.
anything that's in memory is way faster than anything that's on a disk. Um, but I mean, like all caches, if it's tuned to what you do, it's great. And if it's not, then it doesn't help you very much. So picture the scenario where you look at each one of these web pages one time
Right.
and you're not going to go back to them. Well, okay. Well, now I just filled up all my memory with information that I'm not going to look at again. And I can go back and close all these pages and be super diligent about having only one page open, right?
Right.
But that's not really how people work in the real world. People like to maybe go back to things, and people are willing to tolerate a little bit of delay. When I first opened it, it wasn't bad, right?
Right.
Um, so this passive like management of caches, where we just we'll just keep everything until that becomes something we have to do something about. The biggest difference between the one on the right and the one on the left is we are proactively looking at the cache data, and we are using machine learning to make a reasonable prediction about whether or not it needs to stay in memory. Um, Whether or not the impact of opening it again is going to be worse than the
Right.
impact of running out of memory.
Right.
And then we can proactively manage it. So if you see these little dips here
Mm-hmm.
as the graph goes along, we don't really go above this line very much. And that's because we're shrinking the cache data mostly. And in addition to that, there's parts of these applications that aren't really used ever. And that kind of information can be moved into swap, into cold storage. And it's there, it's available if the application needs it. It's predictable to get that data back. But it doesn't need to be in your way, and you can keep doing your job.
Okay, so I've always been told that if it goes to swap, you're in trouble. Why are we putting ourselves in trouble?
Yeah.
Are we doing that?
Yeah, swap gets a bad rap. It really gets a really bad rap. And it's not that swap is terrible at its job, it's that swap is only invited to the party when it's already too late to do anything about it.
Mm.
Um,
It looks like we're getting close to that already on the standard side.
yeah. Um, And basically, like an ounce of prevention is worth a pound of cure, and that's always been the case. That applies in so many aspects of life, right? Um, it turns out that if swap is applied before you're in trouble, it has very small overhead to the system. It can happen in parallel with the stuff that you're doing, the jobs that you want to do, um, and it doesn't really cause any trouble. And it turns out that reading data back out of swap is actually very fast. Um, the trouble lies in when swap has to be invoked and you're already out of resources.
Mm.
So the only time in a traditional system when swap is allowed to do its job is when you're already in trouble and every other resource on the system is now waiting
Right.
for swap to do its job. So of course everybody looks at it and says, man, that's awful.
Yeah.
But if you let it do its job in advance and you don't have to wait for it to do its job, uh, it's actually pretty awesome. And uh, that's what Bitflux is enabling here. Bitflux is enabling uh, like swap to reclaim in advance. We're able to tell it to do its job early. We're able to tell it to do its job intelligently, so that we don't waste time when it matters most.
So just to point it out then, so we're showing that our swap usage is at 1.16 gigs and our used memory is now at 1.55 gigs. So we're in the red, we're over 80%. But
Yeah,
I know that it's going to reclaim and go back under 80%. And we're saying that that is what's going to increase our performance or
yeah.
allow us to do more with little, with less, right?
Yeah, and obviously we're doing the same job on both machines,
Right.
and that's not
And we just reclaimed.
yeah,
We just showed
and
reclaiming.
this is a very clear exercise in showing that the same job can be done on these two machines, and the one on the left has less resources, less memory allocated to it.
Mm-hmm.
Um, so we're technically doing more with less, um, and like experientially, I mean, you ran the test. What did it feel like
Yeah, I mean,
using the two of them?
you can see for yourselves what it looks like. On the right, there's going to be some delays, maybe even starting right now in this tab that's being opened in, I believe it's going to be Instagram. Um, or maybe it's when Twitter Imgur starts. I can't remember exactly, but one of yeah. So you can see there's a delay. There's a delay. It's a normal delay. But as you go further in the process of opening these tabs, you start to see these delays become more and more so. Which as a user, I was like, hey, I'm seeing better performance with Bitflux only because I'm able to open up and not have those delays,
Yeah,
right? And when we open up the ID app after the next couple tabs that'll be open, that'll be really relevant.
yeah, yeah.
We'll see.
What I like about this experiment is it's not really that far fetched for you to come in and turn on your
No.
computer, sit down, and open a few web browser pages.
Right.
And I think that we don't realize how little it takes to put the system into a position where it depends on um, reactive reclaim.
Right.
That's what I would say swap gets a bad rap for, reactive reclaim. And it's astonishing how big of an impact it is and how
Right.
small of like how small the usage needs to be for you to get into that position. And yeah, things waiting for stuff is a pain. And as an end user, I don't want to wait for my stuff to run, right?
Yeah, definitely not.
And in this example, you literally open a few web pages and then you get to work. And by the time you get to work, we're going to see we've hit reactive reclaim
That's right.
on this 4 GB system.
Yeah, you may have noticed that Bitflux like went into the red again, but reclaimed again back to a good used memory amount. And then on the right, standard system, we can see that it hasn't gone down at all. We're never going to see it go down. There's nothing in swap. It's going to continue to get worse and worse as like your experience with using the system will get worse and worse, and then get even worse when swap is open. It's almost like this is compounds, right?
Yeah.
So here's the delay that I was talking about. The Twitter is delaying while we're looking at stuff on the Bitflux side, and that's just going to be what happens from here on out because we're using
Yeah.
so much.
Yeah, we're now getting to the point where
It's constrained.
when we ask for memory, um, the answer to our request for memory is not just yes
Yeah.
anymore on the system on the right. And on the system on the left, even though it has way less memory, the answer to whether or not there is memory available is yes, and it gives it to us right away.
Right.
Um, and that means memory is no longer the constraint on the system on the left. We've minimized it.
Maybe we could speak quickly to like what this means as a developer. Like you jump into something and you can um, immediately begin to use your memory without fear of it um, totally being constrained on you and slowing you down. I think for like just a normal company or business or employee,
Yeah,
saving time.
yeah. The obvious thing is uh, time. Time. I think is the most expensive thing for any business, um, and then that gets compounded by overheads, right? And the overheads would be the cost of your computers, the cost of your compute time, the assets that you need for your developers, those kinds of things. And not only does free memory mean faster development, faster user experiences without changing hardware.
Yeah,
Um, but it means that
which is expensive. I mean, memory is the most expensive, right?
memory is an extremely expensive
Yeah.
component for system refreshes, and I doubt anyone would would be able to say that they haven't had the advice given to them. Oh, your system's slow. Buy more memory. Um,
Pretty common statement.
I challenge you to I challenge that statement now.
Right. Right.
I've done experiments like the one that we are seeing here on a system with 128 gigabytes of RAM, and the same thing happens. Eventually, it slows down.
Yeah.
And I can't tell you how many IT meetings I've been in where our big server with a couple hundred gigs of RAM starts to slow down. Well, I don't know what's happening, and we look and see, oh, there's swap, and then we just reboot it because reboots are easier and cheaper than figuring out what happened, right?
Right.
And now I've spent a lot of time researching what actually happens behind the scenes there, and I think those reboots are completely unnecessary. Um, and I've been able to demonstrate that in several cases, like this one, where managing the caches, avoiding reactive reclaim, um, allows the system to perform. Um, and so this is this will literally be the first time in my life where I would say like, yeah, you can buy less RAM. You need less RAM for that to work, and it's fine.
Right.
You don't need more RAM. Stop buying more RAM.
Yeah.
But I mean, like, buy the RAM that you need to do the job is what we should really be saying. Because applications, I mean, it consumes, right? The one on the left is still using memory, and we still need memory to do our jobs. That's real. Um, uh, and I think that's also one of the biggest takeaways from Bitflux is I can now see what I need to do the job,
Mm-hmm.
and I can understand the limits that I'm facing. So when I'm sizing my equipment for my applications, I can see the data, and I can see how close I'm getting to reactive reclaim, which reactive reclaim I think attributes to is can be attributed to a huge number of system reboots and slowdowns and interruptions and overscheduled resource events.
Yeah. At this point in time, we're coming to the cusp of what the standard systems are going to be able to handle, right? Because we're at 3.48 gigs of used memory. It only has 4. It's not swapping. It's accessing only 13.2%.
Yeah,
Whereas on the Bitflux side, we're seeing, hey, it's actively reclaiming. We'll probably see that come up soon on the used memory dial, and we're accessing 83.6%. That's
yeah,
a huge difference, like in what's happening between the two, and it just goes to show how much, Bitflux is really helping the system. Again, remembering that it's 2 gigs and this standard system is running 4. That's a huge insight for me. I thought that was great when you're talking about memory. It's like that's totally true. Like who doesn't say let's get more memory, right?
Yeah,
Yeah.
everyone has bought their grandma a computer with slightly more memory because it fixes the problem, right?
That's right. I won't have to restart it later. Right. That's
Yeah,
basically
and the secret mystery that reboots actually do make it faster because it clears all this cruft that sits around in your system.
Mm.
Um, yeah, it's just funny.
So we're at 3.7 gigs now on the standard side. And what's going to happen next is I'm going to open that ID app, PyCharm.
Yeah,
And
yeah. So if you look at
first, it's going to reclaim quite a bit
yeah,
of memory on the Bitflux side. And then we're just going to open it
yeah.
up, see what happens.
And I guess I can place your bets, right? of what's going to happen, and you can take the tone of what we've been talking about so
Right.
far and maybe use that to help you with your prediction. But I think it's surprising how big
It
of
was
a difference there
surprising. Yeah,
is.
surprising to me the first time I saw it happen, and when I saw, it wasn't a surprise to me actually when this
Yeah,
happened because I was like,
yeah.
yeah, that's obvious.
And once you start using it for a while, you
Yeah.
start realizing generally everything just feels better.
Yeah.
But this kind of difference. So to put this in a little bit more context, PyCharm. If you look at PyCharm, IntelliJ's website for the recommended hardware requirements for PyCharm, they recommend 4 gigabytes of RAM free to run PyCharm, and as like the bare minimum. And the system on the left only has 2, and we've allocated almost all of it to other stuff.
Okay, start your timer.
Yeah, yeah. So yeah, look the timestamp on the video is 24:23.
Yeah.
And yeah, so we're off to the races, right? So I can actually see code on the one on the left, and I still have a splash screen on the one on the right. And we're going to stop it when the we're done indexing, right?
Yeah, the
So
index is
that's when
going
I
to
can
show up
actually,
here. Yeah.
that's when I can actually use this thing to look around and crossing to code.
Yeah. Now
So we're
ready.
done.
Yeah.
That was 24:52, and the one on the right. Well, I don't know. I think silence says a lot, so I'm just gonna be quiet for a little bit.
Let the counter do its job. Where's the delta counter? I don't believe that the
So it's actually reading the stuff now. So we're updating the index.
oh look, it's updating stuff. That's good.
Yeah. Hooray.
Still not able to use. It's still indexing. The counter's still going. It needs to analyze still. So we're not out of the woods yet with the there it goes, analyzing. Okay. Look at that.
Yeah. Okay. So we'll call that done. And that was 25:47, basically.
So that's like a delta of like about 50 seconds.
Yeah. Yeah. So I waited a whole minute
At a
just for
minute.
this thing to load, right?
Okay.
For one IDE window, like that's yeah, right.
Yeah.
And I mean, like I said before, it's not about having no memory. It's about using your memory as best you possibly can. Both the systems are now pretty tightly constrained,
Yeah.
but the fact that we minimized reactive reclaim on the left clearly had a big difference in the perceived performance of the systems. And if this was a black box and I didn't tell you which memory which one had,
Right.
or what was going on, I like
It hands
take a
down
poll.
easy.
Everybody would be saying the one on the left had more
Yeah.
memory,
Yeah.
just on performance alone.
Yeah.
And I find that hilarious.
Oh yeah.
Just,
No, honestly, like knowing that it took 50 more seconds, that's more seconds, not from when we clicked PyCharm, but from when Bitflux was done. Right. So
Yeah.
like that's very interesting to me. And then, if something takes a minute to open, I'm like, is this thing ever going to open? And I'm clicking around other buttons, which is further constraining the system.
Yeah.
Right. That most people don't realize. And then they're just making it take even longer. And then it might crash. right?
Yeah,
It
yeah,
might, you might lose it,
yeah. So pay attention here for what's going to happen next.
right? We just
Yeah.
reclaimed
So
again.
it just happened, right?
Yeah.
So now what we've done is we've said, hey, you're going to do something again, I'm sure.
Mhm.
So we did the same thing we've been doing all along, and
Yeah.
we're
Reclaiming.
proactively looking at what is extremely unlikely to be used in the future. We're using machine learning to analyze what is happening in the system, and we're moving stuff out of the way so that whatever you do next is going to have available free memory to move on.
And I ran this test and done it for like over an hour on Bitflux running on a constrained system. And it just keeps reclaiming. And I
Yeah,
keep opening things and it keeps
yeah,
reclaiming. And I'm just like, this is mesmerizing almost,
yeah,
like I just want to keep going. I
yeah,
have to like physically stop myself at an hour, but it's pretty interesting.
yeah. And
Very compelling.
so now the memory is basically what this test suggests is that the memory that you require is the memory that what you're doing in the foreground actually requires.
Right.
And like the sort of the evil,
Just kind of pointing out too, like the used
not
memory here, and then
not
like
not the
the
evil.
memory here, right?
Evil's the wrong word, right?
Evil.
But this state that we see over here on the right, this is going to
There's
be
trouble.
pretty constant
Yeah.
reactive reclaim. So pretty much everything you do from this point on is going to have to find memory in this used memory to liberate and to allow you to do the next thing that you want to do. And you're going to have to wait for that every time. Thanks for joining us today. I know this technology is going to change how you view and use memory, and I'm so excited to see how it will help you.
Me too. And we invite you guys to come to bitflux.ai and try Bitflux out for yourself during the free beta.